There we go. And we are now recording, so let me get the screen blown up. Well, there we go. Boom. Okay. As far as announcements go, sort of bad news situation. This is the last of our early classes. Okay, get over it. We will be starting at 8:30 from now on again until something else happens, which hopefully it won't. Do have one other announcement that regards office hours. Normally on Fridays I have office hours from 8 to 12 on the Birmingham West Campus. This Friday I will not be there at all. I've got an infusion this Friday. I have to be at the place at around 7 or something like that. I don't know if I have to be there for blood work this time because it's just at the doctor's, so I got to find that out. But it'll be an all-day affair, so I won't be on campus at all. And even if they do finish early, I go home and go to bed because the Benadryl they give just knocks me out. All right, and here's Thomas Earl. Okay. Yeah, the math majors always drag late, don't they? Okay. Okay. All right, any questions on anything we've covered so far? All right, where we left off last time, we had just finished talking about the 4 statements that all are equivalent regarding zeros of polynomial functions. And here's Patrick. Okay. And then we were ready to move into example 3, but we ran out of time. So how would you recommend that we find all the real zeros of this function? F of x equal negative 2x to the 4th plus 2x squared. Okay? And once we've done that, then determine the maximum number of turning points of the graph of the function. Actually, we could do that right now. Okay? Yeah, well, it doesn't matter. Let's do the zeros first. How would you begin? A little louder? Absolutely, that's what the zeros are. Where f of x, let me get my pen set up. Okay, where that's equal to 0. So I'm going to do it right there, so I don't have to write it again. Then what? That's what defines the zeros of the function. It's where the f of x, and f of x is what, by the way? Y. Where y is equal to 0, those are the zeros of the function. What else is true about where y is equal to 0? Where are you, Waldo, if y is equal to 0? On the x-axis, okay? So all those zeros are also x-intercepts. Very good. Okay? So how do we begin? There's an equation now. It went from being a function to an equation when we set it equal to 0. What do we do with that quartic equation, 4th power equation? Factor, good idea. Okay, and what would you factor?
2x squared.
Okay, I would even pull out the minus sign. Okay, minus 2x squared, and what's left when you pull that out? X squared. Second one?
Minus 1.
Excellent, minus 1. And that's equal to 0. Are you through factoring? Yay or nay? What you think? Can you factor any further? Anybody? Okay. Okay. If this is what you're meaning, yeah, you can, but usually we leave monomials together. But you could say this is a negative 2 times an x times an x. Well, that's not what I meant, but you could do that if you wanted to. I'm sure that's what you meant, right? Say yes. Okay. But my question is, can you factor the rest of it any further? Please say yes. How? Okay.
You're talking about the x squared
Huh?
minus.
Say again?
You're talking about x squared minus 1?
Yes. How does it factor? Or does it factor?
It'd just be x plus 1, x minus 1.
That's it exactly. X plus 1 times x minus 1. And that's equal to 0. Now what do we do? Any ideas? Absolutely. Okay? Anytime you have a series of products equal to 0, at least one of those factors has to be 0, right? Now, can negative 2 ever be 0? Not in this universe. So that one's we're not going to deal with, okay? But this x could be 0, or that x could be 0, but it's still x equals 0, that's one factor. I mean, one 0, okay? Whoa! All right. Now, the second one, or third one, whichever one it is, x plus 1 could equal 0. And what would that yield? X equal negative 1. Subtract 1 from both sides. Or x minus 1 could equal 0. And what does that yield? X equal 1. So we have three possible zeros. So we found all three zeros of the function. Up to how many could we have had? How many zeros could this function have had? 4, because the maximum exponent is 4. The degree of the function is 4. So you could have had up 4, and we sort of did, but these two were identical. So we only had 3. We had x equals 0 and x equals 0. Well, that's just 1, 0. Okay? I don't know if y'all ever watched one of the old Bob Newhart sitcoms, and there was some guy that always came, and he had two brothers. He said, this is my brother Darrell, my other brother Darrell. Okay, this is my 0, x equals 0, and the other x equals 0. Okay, but they were two people. This is only 1 0. Okay, so we found the three zeros. Now, the next question says, determine the maximum number of turning points for that graph. The maximum. We may not have that many, but how many might we have? Up to how many?
2.
Say again?
2.
Up to 2?
Or is it up?
Look the same place you did before and subtract 1. Up to 3. We may not have 3, just like we don't have 4 zeros, we may not have 3 turning points, but we could have up to 3 turning points. Okay? That's the maximum possible number of turning points. I know more people will be coming to keep from bothering everybody up and down the hall. We'll go and close the door. Okay. Now, what they're going to do is graph it, even though they didn't tell us to do it. Let's go on and do that as well. Okay, now I'm going to pull all the pertinent information here. We have x equals 0, x equal negative 1, and x equal 1 are all our zeros. I'm going to pull those out and erase the rest of it. Okay, just because it's going to be hard to read the graph if I graph on top of all that writing. Hope you got it. Okay, so it's gone. Okay. Now, hey. Tegan's here. All right. Now, what else can you tell me about the graph of this function? Is, okay, by that I mean going down, down. Yes. What gave that away?
The negative.
-2 for the leading coefficient. That means, and since it's an even exponent, they're going in the same direction, and since it's negative, they have to be going down. Very good. So we know the end behavior of this function is down and down. Okay? So, use that piece of information. Now let's plot our, we know 0, 0 is on the curve, 1, 0 is on the curve, and negative 1, 0 is on the curve. Let's just tick off a few more points here. All right. Now, normally, there's another very easy point to determine. Normally. Okay? And that would be our y-intercept. What's true about the y-intercept? X equals 0. And what happens when x equals 0? What's your y? It's also 0. But we already knew that because 0, 0 is on the curve. Okay. Get your name, please.
Number 12.
Number 12. Okay. And the name, please? Bree. Got it. Okay. Chikaya. And okay, I know you're in here. There you are. All right. Anyone else come in since I called roll? Okay. So, our other easy point, we've already gotten 0, 0, the y-intercept. Okay, let me go on and erase the 0 here so it won't be confusing. Okay. Now, what they will recommend, I don't think we've gotten there yet, but what we will recommend later is to plot some test points. Okay? And what you usually do there is use your zeros, what we have already, and look at something to the left, in between, and to the right of those zeros. Okay? And pick some points and go from there. Let's just use what we've got already because they didn't really tell us to graph it. Let's just make an estimate here. And actually, the only point I'm really interested in is plus 1/2 and minus 1/2. But time out. What else can you tell me about that function? Just looking at it. It's an even function, which means what? Not the origin. The y-axis, exactly. Odd would be across the origin, even would be here. So basically, if we find out what happens at plus 1/2, we don't have to figure out here. It's going to be the same value. Just like here, it's a 0. There's a 0, but there's on the opposite side is a 0. So this is an even function. We can use that to our advantage. So let's use 1/2. Ooh, that's going to be sort of nasty, but let's do it. Okay, I think I'll do it on the screen. When x is equal to 1/2, what is x to the 4th? 1/2 raised to the 4th power. (1/16). So this is negative 2 times 1/16 plus 2 times, and what is 1/2 raised to the 2nd power? 1/4. Okay. Well, this will be, go 8 times, so that's negative 1/8. And this will go 2 times, so that will be plus 1/2. Now, how many eighths is 1/2? 4/8. So this will be negative 1/8 plus 4/8 is how many? 3/8. All right. And here's Ron. Okay. Now, So when x is 1/2, ooh, I didn't mark my y's here, did I? Okay, 1, 2, 3, 4, 5, 6, whatever. -1, 2, 3, 4, 5. Okay, got them. Okay, so if 1's there, 3/8 is just below 1/2. And since it's an even function, it's going to be 3/8 on this side. And it wouldn't be hard to plug that in either, because when you raise -1/2 to the 4th, it's still 1/16. Okay, so those work perfectly. All right, now we've got enough to graph our function. Okay? Yeah. We know it's going down through here. Remember? From the thing. We know it's going up to this point. It comes down, and it has to be going down here too, so it has to turn here and go back up. And the question is, how many turning points do we have? 3 turning points. One up there, one down there, and another up there. There we have it. And it keeps on heading south from there on. Can't turn around and come back up again, because the maximum number of zeros you could have would be 4. We've already accounted for all 4, because the 2 in the middle are repeated. 0 is repeated. Now, that leads to something else that we're going to talk about at the bottom of the page. So I guess I'll wait until we get there. Now let's go on and talk about it now. Okay. Remember, this was a single 0, x equal -1. Whenever you have an odd number of zeros, I can't get there from here. Alexius is here, and I gotta find you. Skylar is here. There you are. Okay. Anyone else come in since I called roll? Okay. Now, if you recall, x equal -1 was a 0. It was its only 0. All right, Cameron's here. Okay. All right. Try this one more time. X equal -1 was a single 0. All right. All right. Here we have Zaria. And Michaela. All right. All right. Again. Okay. X equal -1 was a 0. It was a single 0. In other words, only had one of them. Okay? Anytime you have an odd number of zeros, one would count, then you're going to cross the axis there. We knew it was going downhill here, so I knew it had to cross because that was a single 0. But anytime you have an even number of zeros, like we did here, x equals 0 and x equals 0, 2 zeros there, then it will not cross. It'll come down and kiss the x-axis, but go back up or down, whichever. Does not cross. And this was another odd, only had 1 0 there, so it had to cross. So those pieces of information tell us that, indeed, we did right there. Now, and here's Jake. Let's see if I can reach him from here. I don't think so. Okay. There you are. All right. Anyone else come in since the called roll? Okay. So here we're getting more and more information about how the graph functions. Like I said, we haven't gotten there yet, but we're going to get there next. Okay? So our end behavior told us where the function's going in the long run. Okay? Very large negative or very large positive numbers, it's going down, down, down. Okay? Because even exponent, negative coefficient. And we found there are zeros, since there's one of these that has the cross there, two of these it comes down and kisses there, and here it crosses. Okay. If there were three, just for instance, it would have come up here. If this was a triplicate here, then it would come up here, hang around a little while, but then go on back. In other words, look like a cubic function there. You know how it bends and goes up, keeps on going. 4 would have come down and been flatter and then gone back up. 5 would have, it's just like your functions would be doing. So that's what happens when you have multiple zeros. I jumped ahead to do that. Any more questions on example 3? That was example 3. Let's see how they did it. I probably beat it to death, so it won't take long to see how they did it. To find the real zeros, you are absolutely right. Set the function equal to 0, because the zeros of the function are where the functions equal to 0. That's what it means. The x values for which they are equal to 0. Okay? First step. Second step, factor everything in sight. Okay? And the minus 2x, it's usually a good idea to pull out the minus sign if it's a leading, your leading sign is negative. If you can factor that out, it's usually nice because it's easier to factor what's left. So we see negative 2x squared is the greatest common factor. Yank it out of there. And that's what they did, leaving us at x squared minus 1. Now, you see that can be factored further, and that factors as negative 2x squared. That's the first part, the monomial part. X plus 1 times x minus 1. It doesn't matter which order, but factor it completely. And then, because the whole set of factors is equal to 0, figure out what each one of them is. The real zeros are x equals 0, and that happens to be a double 0 because you have two x's equals 0. Then you have x equal positive 1 and x equal negative 1. Those are single zeros there. Okay? Now, because the function is a 4th degree polynomial function, the most number of zeros you could have had was 4. We only had 3 because that x equals 0 was a double. That really was 4. Okay? But also because the maximum exponent was 4, you had at most 3 turning points. 4 minus 1 would be 3. Then they drew the graph, okay? And we do have the 3 turning points. One local max, one local min, and another local max, okay? Here are our 3 zeros. This single 0, it crosses. That single 0, it crosses. But the double 0, it kisses and goes back up, okay? But those are our 3 turning points. Here, here, and there. Okay. Any questions? Now, they didn't say graph it, but they did, and I showed you how to and some of the keys. They didn't even mention the end behavior. That's a good thing to do it first, see where it's going in the long run. All right. Now, if you noticed in that example, because I harped on it forever, the exponent is greater than 1. Okay, we didn't say that. The factor negative 2x squared yield what we call a repeated 0 at x equals 0. We had x equals 0 and x equals 0. 2 of them. That's repeated. All right. Second, yeah, okay, I got it. Don't hear well, sorry. 10, all right? All right. Anyone else come in since I called that? Okay. We call that a repeated zeros. Now, here's what I was talking about on it. Anytime you have a factor, this is x minus a. Now up here, it was just x squared. But x minus a to the kth power. What was your a here? I don't see an a. What was it? If you don't see it, it was probably 0. X minus 0 squared. You could have written it that way if you wanted to. That meant at x equals 0, you had 2 zeros there. Okay? X equals 0, you had 2 zeros. It's called a repeated 0 at x equals a. Now, the other thing we say, it has multiplicity of 2. Now, they never say this, but the others are multiplicity of 1. If you only have one factor, then that's a multiplicity of 1. Not much of a multiplicity, okay? They usually reserve this for k greater than 1 to say multiplicity of k. But I go on and include 1 because it makes sense, it seems to me. When k is odd, meaning it's 1 or 3, 5, 7 of any of those, the graph crosses the x-axis at that 0. When k is even, 2, 4, 6, 8, whatever, the graph touches the x-axis there, but does not cross it. If it's on the upper side coming in, it's on the upper side going out. If it's on the lower side coming in, it's on the lower side going out. It touches, but does not cross. Okay? So that's what multiplicity tells you. If you have a multiple 0, a repeated 0, x minus a raised to some power k, then that has a multiplicity of k. Now, the book doesn't do it, but I say if that is a single 0, I say it has a multiplicity of 1, which really doesn't make a lot of sense, but it follows the same pattern. It crosses there. Okay? Now, to graph polynomial functions, use the fact, flip a page here, use the fact that the polynomial function can change signs only at its 0. Now, why is that true? Why is it true that the function can only change signs at its zeros? What were the 2 characteristics of the graph of a polynomial function? Say again? Okay. Okay, that's what that gave you. Okay. They are smooth and continuous. So if you have a smooth and continuous function, how can it ever change signs unless it does it at a 0? Because above the x-axis it's positive, below the x-axis negative. Because it's smooth and continuous, it can't jump over it. That wouldn't be continuous. Okay? So it has to cross there, and that's the place where it changes signs. So use the fact that polynomial functions can only change signs, only at the zeros. And between 2 consecutive zeros, here and here, they can't change signs. It has to be either positive or negative. Okay? Because if it changed signs, there would be another 0 in there. Because polynomials are smooth and continuous. Mostly that they're continuous, but I like to always put both of them together. Okay. What that means is that when you put the real zeros of a polynomial in order, they divide the real number line, which is your x-axis, into intervals into which the function has no sign change. And here's Walter. Or Walt, sorry. Okay? And here's Reggie. Okay. Anyone else come in since I called the roll? When you hear me call your name. Now. All right. Those resulting intervals are called the test intervals. And we did that. Remember? We had an x at 0, a 0 at 0, and a 0 at 1, and we chose 1/2 in the middle, the test to see where the function was. And then we knew that it was only going to be, since it was positive there, it's only going to be positive in between those 2 consecutive zeros. Okay? So we call those our test intervals to determine whether the value of the polynomial function is positive, graph lies above the x-axis, or negative, lying below the x-axis. Okay? Now, it appears to me that they're skipping examples 4 and 5. And by the way, I didn't say before, after example 3, there was a checkpoint. There's a checkpoint after every example, and you can find audio, video solutions to those checkpoints at larsonprecalculus.com. An absolutely free website. You don't need a code of any nature to access it. Just go to that website and follow the links. So let's do example 4. Let's go back and find some white space. That looks like a good amount of white space. And it says, sketch the graph of the function f of x is equal to 3x to the fourth minus 4x cubed. F of x equals 3x to the fourth minus 4x cubed. All right, here's Cody. Pardon me?
Can you fill that out?
Okay, at the end of the class? Okay. Okay, remind me so I don't forget it. Okay. All right, I'll get Cody marked here. All right. Anyone else come in since I called roll? Okay. I think that was my function. F of x is equal to 3x to the fourth minus 4x cubed. Okay, they say sketch it, so I'm going to go on and draw my axes. Don't know if I allowed enough room, but we hope so. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5. I hope we won't go much further south than that. If we do, it'll be Cody's fault. Okay, now, what's the first thing you think you ought to note about that function? Anything? Excuse me. What should you note about the function? First thing, probably going to help you graph it. Say again? What's positive? I think you're right. What do you mean positive? It's a very positive function, yes, sir. Yes, what's that? It opens upward, very good, because that's what we call the end behavior. That's what that was supposed to mean. Because the maximum exponent is 4, it's either on the up and up or down and down. It goes in the same direction. Because the leading coefficient is positive, it has to be on the up and up. So, we know the end behavior. Always a good thing, if you're graphing the function, good thing to note first is where it's going in the long run. This long look, no, that's commercial. Okay? It's on the up and up. Okay? Now, what would be the next thing you might do to it? Say again? Anyone say something? Okay, set it equal to 0. Another great choice. Set it equal to 0. Why would we set it equal to 0? We're looking for the zeros of the function. So what do we do to find those zeros of the function? That's now an equation. If you sort of ignore that part, that's an equation. And what can you do with a polynomial equation? At least try to. Factor it, okay? And what factors do you see from that? X cubed is the only monomial factor. What does that leave us with? 3x minus 4, and that product is equal to 0. Okay? Where do we go from there? Everybody see that? Why we did it? Okay, where do we go from there? Set them equal to 0. So either x cubed is equal to 0, or 3x minus 4 is equal to 0. Why is that? Because anytime you have a product of however many entities you have equals 0, one of those has to be 0. There's no way around it. So either x cubed is 0 or 3x minus 4 is 0. Now if x cubed is 0, what does that tell you? If x cubed is 0, what number can you cube and get 0 as an answer? 0. So x has to equal 0. But that's what kind of a 0?
Double 0.
It's not just double. Triple 0. Oh my goodness. Here is Ryan. Okay, good deal. Anyone else come in since I called it off? So it's a 000, meaning it has a, what's that new word we had? Not new, but multiplicity of 3. And 3 is what kind of number? Odd, which means it's going to be crossing the x-axis at x equals 0. So it's x equals 0. We're going to have 1. Let's go to the other one. What do we get from the other equation? What would you do with that? Add 4 to both sides. Solve for x. Okay, that gives us 3x. These add to 0 is equal to 4. Divide by 3, and that gives you x equals 4/3, which is 1 1/3. There's our other 0. And what happens there? It crosses the x-axis there as well because 1 is odd. That's a single thing. I call it multiplicity of 1. The book doesn't, but it works, okay? So it crosses there. Now, we already know the shape of this function. If it's coming down from here, it has to be coming in here, crossing here. But because there's 3 of those, it comes down here and acts a little like a cubic function. So it hangs around the 0 for a while because there's 3 of them. You know, 3's company. Somewhere here it turns around and crosses again going here, and because the end behavior is up here and up here, there ain't no more turning around. Okay, that's all you got. Okay? So it looks like for this one, we're only going to have 1 turning point, even though we could have up to 3 turning points, but we're only going to have 1. And here's what happened to the other 2. They merged into 1. You see, this was wanting to turn and then turn and do like this, but because all those zeros are the same, they just sort of smudged together there. So we're going to wind up with 1 turning point. Now, to me, we could just go on and plot the thing, okay? But, Trees, I thought so, okay? Okay. There you are. Okay. Anyone else come in since I called roll? Okay? Excuse me. Okay. Now I know what the book wants us to do. Pick some your favorite things. Test points. Okay? Let's pick some test points. What would you choose as a logical test point? 1 will be a great one because it's in between the 2 zeros. -1 because it's to the left of the last 0, and 2 because it's to the right of the first. Okay, left of the first 0, right of the last 0. Okay, and 1. So let's choose all 3 of those and figure out what our values are there. Okay, you need to know what your values are. Okay. Sounds like a politician. No, okay. All right. There's your function. Let's plug into that function f of, which one you want to do first? I don't care. -1. F of -1 will be 3 times what? How do you do f of -1? Say again? -1 to the 4th power. Minus 4 times -1 cubed. Okay? Now, what's -1 to the 4th power? Positive 1. Any negative to an even power is always positive. A positive to even power is always positive. Positive to any power is positive. A negative, if it's to an even power, is positive. Odd power, negative. So this will be Positive is 3 times 1 minus 4 times, now what's negative 1 to the third power? Negative 1, because that's an odd power. Okay? And 3 times 1 is 3 plus 4 equal 7. Goodness, I didn't leave enough room, did I? Did I do that right? I think so. Okay? Way down south. Okay? It goes way down here before it turns around and comes back up and crosses there. I didn't leave nearly enough room. Okay? Now, there is our at negative. Oh, wait. Y'all are confusing me, aren't you? Okay? This is at negative 1, not at positive 1. What are y'all doing? You're trying to lead me astray. This is a positive 7. 1, 2, 3, 4, 5, 6, 7. There it is. At negative 1, it's a 7. So look at that. Coming down here like that. Okay? And going up forever in the opposite direction. Now let's do our other one. And what was that one? Alpha of? Next test point? 1. That's going to be pretty easy. Can I tell you a real easy way to do ones? Do you mind? Y'all don't like easy, do you? Okay? Because 1 raised to any power is going to be 1 raised to any power is going to be 1. So add your coefficients. Right? Because the exponents, the variables are all going to be 1. No matter what power you raise it to, it's going to be 1. So what is the sum of those coefficients? Negative 1. Okay? That's the one that goes down here. I didn't think I had botched up that badly. A negative 1 here. Okay? Now, I'm guessing it goes south of there and comes back up. Okay? Now, one thing we know, it has to be smooth. So don't make that a point. Mine's probably a little too pointed, but it has to be smooth. I don't know how far it goes down, and I really don't care. But it probably goes further south and then comes back up, because that's so close to 1 1/3. Okay? So there's our second test point. What's our third one? Okay? Alpha of 2. And what would that be? Alpha of 2. 3. 2 to the 4th power. Go on. Minus 4 times 2 to the 3rd power. And what's 2 to the 4th power? Already got it once today. Say again. 16 minus 4. What's 2 to the 3rd power? 8. Okay. So this will be 3 times 16 is 48 minus 32 equals 16. Off scale. So at 2, we're way up there. So this is not just going through here, it's going way, 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 way north. Okay. So that's how it looks. So let me take off a little bit of the extraneous stuff here. Yuck. Get out of there. Okay. Okay. I can take off that one, and probably that one, and that one, and that one. So this is more how it really looks. The end behavior is on the up and up. We see that. We've got zeros at 0 and 4/3, or 1 1/3. The one at 0 is an odd multiplicity, so it hangs around there a little while, makes a little bend there, but then heads on south. It has to cross, and it goes through the next test point, and then moves on to up to the other 0 and heads north really, really fast, because the action is dominated by x to the 4th, and that drives it up. Any questions on that? Now they show it minimizing awfully close to x equal 1, so I may have been wrong on that. Maybe that's going to be the minimum. We can't tell from that here, but it's going to be something close to that. All right, there is a checkpoint. Please do the checkpoint. Okay. All right. Now, it seems like there should be some verbiage before they hit example 5. They don't do it on the slide set. So let me read it to you. I sort of don't care for this too much, but it's okay. A polynomial function is in standard form when its terms are in decreasing order of the exponents from left to right. Okay? Now, that's with the exception of what? Quadratic functions, their standard form are different. We did that earlier in the last section. But for all higher order polynomial functions, they're in standard form when they're in decreasing order from left to right. Okay, so let's go to, let me scratch all this, and sketch the graph of this function. Oh, this looks like fun. F of x is equal to minus 9/2, yay, x plus 6x squared minus 2x cubed. Oh, what a joy. Okay? It says sketch the graph of it. So I'm gonna draw my lines, my axes. I'll even tick off a few points. That means make them angry. Okay. Okay, something like that. Okay, I don't have them very nicely spaced, but get over it. Okay. What's the first thing you're going to do to that function before you graph it? Well, I don't know. You tell me what you're going to do first.
See that they have a maximum.
Say again?
You can look at the sign.
Say again?
Leading coefficient. Look at the sign.
Okay, what's your leading coefficient?
9.5.
Oh, yes. Okay, never mind. Yeah, it's not in standard form. Didn't you sort of guess? Since we just talked about it, maybe they would give you one that wasn't? Okay, what is it in standard form? Negative 2x cubed. So you're right, it does have a negative leading coefficient. It's just the wrong one. Okay, next. Plus 6x squared minus 9/2 x. Okay. There is a function written in what they're calling standard form. Decreasing order of the power. 3, 2, 1, 0, blast off. Okay, we got it. Yes?
We're going to eliminate an x.
I'm sorry?
We're going to eliminate an x.
Okay, excellent. Excellent. Okay, all right. I'm sorry. No. Okay. We're going to factor out an x, yeah, or eliminate one as he wants to call it. Okay. Now, I want to do something else with it at the same time. Now, I can do it now, or we can do it later. And maybe later would be easier. So let's just pull out the x now. Since that's what he told me to do, let's just do that. So factor out an x, but I also want to do this for sure. The negative. I want to factor out the negative. Wait. Time out. Before we do that, let's talk about, say again? Say again? Okay, domain for polynomial functions is always what? All real numbers. Okay? What can we do looking at this function? What's the first thing we ought to note? Which way it's going when? Yes, for very large numbers. That's what in behavior means. For very large numbers, what is this function doing? So you tell me. For very large negative x's, where is it going? Okay. Give me a large negative number, but don't make it too big. Maybe 10. Okay. Okay, negative 10. What's negative 10 cubed? 1,000. Negative 1,000. And then multiply by negative 2? Positive 2,000. Now that looks like it's going north to me, right? Okay. What if you had a very large positive number. Ew, it's going south really fast because this would be, if it's 10 again, that would be 1,000, and that would be negative 2,000. JT's here. Okay. They stand outside waiting till I'm over there to come in. Okay. All right. JT is here. Has anyone heard from Ed? He was perfect attendance for so long, and we haven't seen him since. What's that? Ed Adamson. He sat right up here, I think. Yeah. What's that? Yeah, well, on that side, or maybe there. Somewhere he sat up near the front. Yeah. Okay, but we haven't seen him in forever. Okay. So, what we've got for our end behavior is when x goes very large negative, it's going upward. And when x goes very large negative, a positive, it's going downward. So there's our end behavior. Always a good idea to note that first. Okay? Next, we were going to factor out something with the x. Anyone want to make a suggestion of what we pull out with the x? You suggested the x. I want something else. Okay. Okay. Let me do another timeout here. Okay? Actually, before we start factoring, we ought to set this equals 0. Yeah, we ought to do that first because we only factor equations. We don't factor functions normally. I mean, we could. But let's factor the equation. Okay? Now, I suggest you factor out the negative sign too because I don't like starting off with a negative number. It's so negative. So let's factor out a negative x. And what do we have left? Whoa, where are you going? There we go. Okay. What have we got left? 2x squared. Say that again. Wait a minute. Wait. X is here, and I was over there. Okay, never mind. Okay. Say again. Minus 6x plus 9 halves. And we're going to set that equal to 0. Okay? Good deal. All right. Now, the bad news is, the good news, I know what 1, 0 the function is. Can anyone tell me? X equals 0 from this one. X equals 0. The other one, though, is a little messy. I'm going to write it down by itself over here. 2x squared minus 6x plus 9 halves is equal to 0. Folks, I don't know how to factor a polynomial that has a fractional form. That's pretty miserable. Okay? But since it's equal to 0, what can we do? Say again? 0.0. What you mean?
Plug it in.
Oh, plug in a 0. Okay? Well, that gives you when x equals 0, that function is equal to 9 halves. But that doesn't really help us because that's not the original function. It's a good idea, but it's just not very helpful here. There's an equation, and if I can't factor if it's got fractions in it, what can I do? Can't I multiply both sides of the equation by the same number? Because that's an equation, right? It's going to be an equivalent equation. What number would you choose to multiply by? 2 to get rid of that denominator. So let's multiply this by 2, this by 2, this by 2, and we'll even multiply that by 2. Okay, and what does that give us? 4x squared minus 12x plus 9 equals 0. Ha! Got it. Okay. Now, does that look at all suspicious? What's that? Does it look a little familiar, like maybe we've seen something like that before? What? It's a quadratic equation, yes, okay, as maximum exponent of 2. You're absolutely right, okay? Is it any special kind of quadratic equation? Okay, what we're trying to do is factor, right? What would be your first guess of factoring that? If it's factorable, we don't know that it is, what would be your first attempt? What's one possible factorization of 4x squared? 2x times 2x. I like it. Okay, then where are we going to look next? Oh, we have another O here. Okay, what did you find?
Nothing.
Yes, you did.
I didn't realize what we were doing.
Huh?
I didn't realize what we were doing.
Oh, okay. All right. Where do we look next?
4 and 1.
We could do 4 and 1, but let's stick with 2 and 2 first. And, okay, you look at the sign of the last term, it's a positive. What does that tell you about these two signs?
3.
Okay, so both negative because the middle's negative. Minus 3 and minus 3. All right, I think I'm pulling teeth now. Okay. Does that work? Yes, it does. 2x times 2x is 4x squared. 2x times minus 3 is minus 6x. Minus 3 times 2x is minus 6x, and minus 6 times minus 6 is minus 12x, and then that is plus 9. Yes, we have a happy face because we found the answer, okay? So, what does that mean? There's our other... What's that? Set them both equal to 0. So, 2x minus 3 is equal to 0, or... they're the same thing, aren't they? So if we get one, we're going to get the other one. What is it going to be? Second? X equals 3 halves. You went right to the 3 halves. I can't write. Yeah, you add 3 to both sides, divide by 2, right? Yay? Okay. And the other one's going to be x equals 3 halves too. So what do we call that? Multiplicity of 2. It is even, but it's multiplicity of 2. That's an even number. A repeated 0. Call it all sorts of things. So here we have x equals 0 again. Now, not all of them are going to have x equals 0 as a 0, but this one does. And 3 halves is right there in between 1 and 2. 1 and a half. But that's a double 0, right? Which means what? It's what? It is going to cross or doesn't it? A double 0. Yeah, if it's even multiplicity, which you pointed out to me, it's not going to cross. This is a single, so it's going to cross. And since it's crossing and has to come from up high because its in behavior is positive, it has to be coming down like this, and it's gotten below the x-axis here. It must come up and kiss it there and then go down. So that is my guess of how it's going to look. Okay? I shouldn't really do that, but I'm just pretty lazy. I don't really like to do the test points. So let's do some test points. What test points would you think would be beneficial? -1. So x equals -1. Any others? 2 and 1. Yes, let's do those 3 test points. In the original equation. Ooh, okay. So I think I'm going to erase a bunch of stuff, if that's okay, because it's just going to be too messy. So let's erase all this. We've used it. I want to leave that, okay, because that was my original. I'm going to erase this because we don't need that anymore. We've used it. I erased my x equals 0. I didn't mean to do that. But we've already got it plotted, so we're okay. And I think we can erase all this. Okay, I don't want to erase my end behavior. All right. I shouldn't have erased my zeros, but I did. Okay, we got them plotted. All right. So here's our f. So let's do f of minus 1. What is that going to be? Positive 9/2. She did that just by thinking negative 9/2 times the negative 1 is going to be a positive 9/2. Next, plus, or is that minus? Second? Plus, because you're going to square the minus 1, which gives you plus 1, so that's plus 6. Second, positive 2. I think that's pretty positive, don't you? Okay. 9/2 is 4.5, and then you do another 6 to it, that's 10.5, and another 2 is 12.5, so that's way on up there, folks. Way up there, okay? Off scale, okay? It comes down to 0. Let's do it at positive 1. So what's f of 1? And remember my little trick? No, okay. Just add the coefficients. Because all the x's are going to be 1, right? When x equals 1, x to any power is going to be 1. So that's going to be minus 9/2 plus 6 minus 2. So 9/2 is minus 4.5, right? And another minus 2 is minus 6.5, right? Yeah, no, minus 8.5. Ooh. Minus 8.5 plus 6 would be minus 2.5. So it's way down here. So I didn't get it anywhere close. Okay, so it's coming down here and probably coming back up here and going something like that. Okay. Oh, let's see what it is at 2. I'm sorry?
Minus 4.5 plus 2 is 2.5 minus 2 is 1/2.
Oh, I'm sorry. Let me.
Minus 4.5 plus 6 is 2.5.
You're right. 2.5. Wait. All right.
You get minus 4.5 plus 6. That's 2.5.
Oh, you're right. Minus 6. Okay. I had it minus 1/2 in my head, and then I talked myself out of it. So let's erase this, and that's minus 1/2. See, my drawing was right. You're proving me right. It's right there. At positive 1, it's minus 1/2. Look how close I was. Okay? Now, at 2, what do we have? Minus 9, because the 2's will cancel out, plus 24 minus 16. All right? That's, what is it? Minus 1, isn't it? Oh, look at my graph. Wasn't that wonderful? Okay. All right. So I wasn't far off. Way off, but not far. Okay. So this is way out of place. It's going downhill this way and going uphill that way. Okay. There it is. Something like that. Now they have it, oh, nah. They picked some other weird point. They chose positive 1/2 and minus, oh, I wish I had chosen fractions. They're easier to work with. No, I'm just kidding. Okay, there is a checkpoint there. Please do the checkpoint. All right. Any questions on those? Okay. Now, let's move on to there we go. Intermediate value theorem. And we have come so close to doing it already, but here's what it is. The intermediate value theorem implies that if you have 2 points, x equals a, then of course the y would be f of a, right? And x equals b, the y would be f of b. So if you have 2 points, a f of a and b f of b, there are 2 points on the graph of a polynomial function such that f of a, the y value here, is not the same as this y value there. They can't be the same. They've got to be different. Okay? Then for any number d, that's in between f of a and f of b, any number d in between that, there must be a number c in between a and b that such that f of c is equal to d. Okay? Blah, blah, blah. Okay, what in the world does that mean? If you have a polynomial function, tell me two characteristics of the graph of a polynomial function. Say again? A little louder? Oh, it was at least 25 minutes ago. Smooth and continuous, not constant. Continuous, okay? Smooth and continuous. That means there's no breaks in it, okay? It has to go through. So if you have an A here and an F of A there, that's fine. A B here and an F of B somewhere other than F of A, okay? Then for any value in between the F of B and F of A, that value D, there has to be some value C in between A and B such that F of C is equal to D. And why is it? Because polynomial functions are continuous. You can't get from here to there without going through every point in between. So that means there's got to be some value C so that F of C is equal to D. If D is in between the Y's, there has to be a C in between the X's that fits that form, that function. Okay? That kind of makes sense, doesn't it? Okay. All this makes sense, right? Okay. Is there only one point? Not necessarily. This would have been a smooth and continuous function, right? It could have had two or three of those in between, but there's at least one that will pass through D. Okay? See, I had 1, 2, 3. Okay. Whoa, okay. Now, didn't we just do that? No, okay. Here it is printed out in a box. That makes it more important. Intermediate value theorem. Let A and B be real numbers such that A is always less than B. And if f is a polynomial function such that f of A is not equal to f of B. F of A could be greater than f of B. That's fine. Then in the interval A to B, f takes on every value between f of A and f of B. Every one. Okay? Now, it may take on some that are outside f of A and f of B. It could go up and down, but it takes on every value that's in between f of A and f of B. So what? The intermediate value theorem helps you locate the real zeros of a polynomial function in the following way. If you find the value x equal A, at which the polynomial, say, is positive, and you find another value, x equal b, where the polynomial is negative, you know there's got to be at least one zero in between, because you can't get from positive to negative without going through the x-axis. Not if the function is continuous, and polynomial functions are always continuous. So therefore, it's got to go through at least once. Okay, you can conclude that the function has at least one real zero in between those two values. If one's positive and one's negative. Now, if both of them are positive, no guarantee of anything. Or both negative, no guarantee. But if one positive, one negative, or vice versa, there's got to be a zero in between. At least one. All right. Now, okay. And by the way, folks, we talked about this earlier before. Most of you were here. How sad it was that we won't be starting at 8:15 anymore. We'll be starting at 8:30 from now on. Okay, get over it. Okay. All right. Now, she just turned it in. You started at 8:15 today? Yes? Okay. Now, and someone else said we're not starting at 8 today? I won't call any names, okay? Okay. So, here's a function. Anyone think you can find the zero right off the top of that? Even if that was a quadratic function, it would not have a factorable zero. You could use the quadratic formula on it, though. But on this one, cubic, man, we don't have any way to do anything with that. So what we might try to do is plug in some values. Okay? What's the easiest x to plug in? 0. And alpha 0 is equal to what? 1. Okay? That's positive. Okay? Now, if I plug in any positive value past 0, all of them positive values past 0 that way, these are going to be positive. And this is going to be greater than 1, right? So let's look at something to the left of 0, like minus 1. What happens here? Negative 1, 1, 1. That's still positive, but it's 1. Let's go another one down. Negative 2. What would that be? Negative 8 plus 4 plus 1. That would be plus 5. That would be a negative 3. So obviously there's got to be a 0 in between negative 2 and negative 1. And sure enough, there has to be 1. We just don't know what it is. And I'm going to make a guess. It's not negative 1.5. I'll just say I don't think it is. It may turn out being that, but I don't think so. So it follows from the intermediate values theorem that says at negative 2, the function is negative. At negative 1, the function is positive. There has to be a 0 somewhere in between negative 2 and negative 1. There could be more than 1. Don't think so. But there has to be at least 1. Okay? Now, I'm going to extend this something else. If this function is has degree odd, 5, 7, 15, any degree like that, what can you tell me about the end behavior? Opposite each other. Either like this or like that. And guess what? There's got to be a 0. Now, evens, there may or may not be any zeros, but odds, there will always be at least one 0. Maybe many more, okay, but there's going to be at least one, okay? So, anyway, here we have, and we know there has to be at least one 0 in between that, okay? Now, so by continuing that line of reasoning, you can approximate any real zeros of a polynomial function to any desired accuracy, and that concept is further demonstrated in example 6. So let's do example 6. Slightly different function here. I was going to do it with the one they gave us, but they didn't do it, so we won't either. Let's do example 6. Top of page 131. Okay? All right. Let's pick a couple of things. What's the real easy? Okay, alpha 0 is equal to 1. Okay. Let's go either right or left. You decide which. Say again? At 1, so let's do alpha of 1. And what will that be? Just add your coefficients. It's still 1. And if I get any larger, this is going to take over, right? That's going to dominate. It's going to get positive, positive, positive. So let's go to the left. Alpha of minus 1. What does that give us? Say again? Negative 1 cubed is negative 1 minus negative 1 squared is 1 plus 1. What's that? Negative 1. Ding, ding, ding. We have a crossover. At 0 is positive. At negative 1 is negative. So we know there's got to be a 0 in between 0 and 1, negative 1. So guess what? Let's pick a point in between 0 and negative 1. Pick one. 1/2. Let's do 1/2. Let's do f of 1/2. Okay, what's 1/2 cubed? Oh, wait, it's negative 1/2, right? Okay, negative 1/2. It's what? Cubed would be negative 1/8. Is that what you said? I thought so. Okay. All right. Minus 1/4 plus 1. And what does that yield? Well, negative 1/8 and negative 1/4 is negative 3/4, plus 1 would be 5/8. Right? Y'all check me on that. Believe I'm right. Positive, right? So now I've got something closer to 0 than 1 was. Okay, we're throwing this one out altogether, than 1. So now let's pick something in between negative 1/2 and negative 1. At some point here, folks, I think you're going to find it a little easier to start using decimal numbers, because you can do that in a calculator really easily, right? So f of something between negative 1 and negative 1/2. Negative point what? 3/4, you said? Yeah. Okay, he's staying with decimal fraction. We can do it. Negative 3/4. Okay? And this would be 3/4 cubed. Of course, it's still going to be negative because it's odd power. That would be 27/64. You chose it, didn't you? Okay. Yes, Now you tell me. Okay, minus. Okay. How about 0.7? Would that be a little better than negative 0.7? Now, y'all going to have to pull out your calculators, okay? Okay, I saw a quick draw there. Okay, pulled out the calculator. Whoa. Negative 0.7. Okay? Now, in your calculator, do negative 0.7 cubed minus 0.7 squared, which would be 0.49. I know that one. Plus 1.
0.167.
Say that again.
0.167.
Okay, still positive? All right, we're still positive. Okay? And we're even closer to 0 than we were at negative 1/2. But we're still positive, so we need something in between negative 0.7 and negative 1. What might we choose? Say again? Between negative 0.7 and negative 1. How about 0.8? That do? Plug that in your calculator. Negative 0.8 cubed minus 0.64. I know what 0.68 squared is. Plus 1.
Negative 0.152.
152. Okay, so now we've got something in between negative 0.7 and negative point. See, this one's positive, that one's negative. I'd go, now your choice before was probably pretty good. F of negative 0.75. That's what you had said, and you probably would have been pretty good. Okay, negative 0.75 cubed minus 0.75 squared plus what?
0.015625.
Okay, that's getting pretty close to 0, wouldn't you say? And you could keep dragging it out, they ultimately go into continuous until you get negative 0.755, they say. And that's going to be awfully close to 0, but not exact, okay? So you can get any accuracy you want, but just keep the window in between. You see, this time you would go in between 0.75 and 0.8, negative 0.75 and 0.8. So I would have probably done negative 0.77 because it's in between those without doing too much, and that's what they did. No, they said 755. So it's much closer to that. So, but you can keep the brackets going until you get as close as you want. I call that the method of exhaustion. Okay? Actually, Archimedes called it something like that much earlier. But, after a while, that's close enough. I'm tired of doing it, so get as close as you want to get. Okay? There is a checkpoint there, and that finishes 2.2. We've got time to do The vocabulary is 8 questions here, so let's get to it. Any questions before we start doing these questions? Okay. The graph of a polynomial function is blank, which means that the graph has no breaks, no holes, no gaps. Continuous, exactly. Number 2, the blank, blank, blank is used to determine the left-hand and right-hand behavior of the graph of a polynomial function. Now, the book calls it one thing, I call it a different one. The blank, blank, blank determines the end behavior. The what? No, that's what you're determining. The test, I'll give you the last word is test. I think it is, let me think. Yeah. Leading coefficient test. That's what the book calls it. I prefer to call it the leading term test because you use the whole leading term, not just the coefficient. Coefficient is part of it, but you use the whole term. Okay? Okay, number 3. A polynomial function of degree n has at most how many real zeros? A polynomial function of degree n has at most how many real zeros? Say again? N. Okay. And at most, how many turning points? N minus 1. Not n minus 0. N minus 0 would be n. Okay, n minus 1. Okay, good deal. Number 4. Okay? When x equals 0, when x equal a is a 0 of a polynomial function f, the 3 statements below are true. X equal a is a blank of the polynomial function f of x equals 0. Second, I think the word they're looking for is solution. It'll be something like that. Number B, blank is a factor of the polynomial f of x. How would you express? X minus a would be a factor. Perfect. And the point A0 is an blank of the graph of f. X-intercept. Perfect. Okay, number 5. When a real 0 x equal a of a polynomial function f is of even multiplicity, the graph of f blanks the x-axis at x equal a. Say again? Not if it's even. Touches, but does not cross. Okay? And when it is of odd multiplicity, the graph of f crosses the x-axis at x equal a. Perfect. Number 6. A factor, x minus a raised to the kth power, as long as k is greater than 1, yields a blank blank x equal a of blank k. A lot of blanks there, right? Did you draw a blank? Never. Okay. If it's a factor, then it is also a, go back number 4, it's a 0. What kind of 0? Repeated 0. There's the blank blank, x equal a of multiplicity k. Excellent. Number 7. A polynomial function is written in blank form when its terms are written in descending order of the exponents from left to right. Standard form. And number 8. The blank blank theorem states that if f is a polynomial function such that f of a is not equal to f of b, then the interval a to b, takes on every value in between f of a and f of b. Intermediate value theorem. Okay, perfect. Okay, now I think I've said this several times before. I'm going to say it again. I would do all of 9 through 14. Okay? It's matching the functions with their graphs. That's a good exercise. The odds will be found in the back of the book or at calcchat.com. Then do either 15 or 17 or both. They're both at calcchat.com. 17's at calcview. Do any of the odds 19 to 23. They're all at calcchat. 21's at calcview. Do either 29 or 31. They're both at calcchat. Do any of the odds 33 to 47. They're all at calcchat. 43's at calcview. Do either 49 or 51, or both. They're both at Calc Chat. Do any of the odds 53 to 61. They're all at Calc Chat. 59's at Calc View. Do any of the odds 63 to 69. They're all at Calc Chat. 67's at Calc View. Do any of the odds 71 to 83. They're all at Calc Chat. 73's at Calc View. Do either 85 or 87. They're both at Calc Chat. Do either 89 or 91. They're both at Calc Chat. 89's at Calc View. And then do any of the odds 93 through 97. They should all be at Calc Chat. There are 2 true false, 99 or 101. They should be at Calc Chat. Then there are some modeling problems, and that would be 103, graphical reasoning 105. You can think about doing 107 if you choose. And I guess that we are just about out of time. So we'll start next time with 2.3. And after we finish 2.3, you know what we get. A quiz. So I'll try to have that ready for you next time, just in case you want to start early. What's that? I have graded, I'm trying to think, probably about half the test. What I'm doing, I'm tied up with doing schedules for fall and spring and summer, and it just has tied me a knot. I hope to finish that today if I can, and then get back to grading. Huh? Okay, what's your name again? Oh, you're Z. I put you on the wrong one. Okay. So, Kiana didn't make it in, right? Okay. All right, good deal. All right. All right, let me get this put away so I don't forget where I am or who I am or what I am.
See you Thursday, Mr. Fallon.
All right, take care. Okay. Now, Odie Wong, right?
You just gotta do it once for each one.
Okay, class is math 1, 2. Oh, all it needs is a grade. I thought it needed the other stuff. Okay.
No, you need it. I have to do, grade. And then, you don't have to do that because we haven't really done anything for that. But the absence tardy, just write,
Okay.
if it's good or bad.
Yeah.
Kind of like that.
I don't know for certain, but I'm going to say a C. That's going to be okay. It's a high C. It's 78 because I don't have your tests graded
Oh, okay.
all the way. So I'll put that test quiz.
Can you put one dash, one test or something grading?
Okay. How about
Just
C
put it
plus?
there.
Is that okay?
Okay, that's fine.
All right. 78. Okay. Absent tardy. Is this all the way or for how long?
Just write if it's good or bad, I guess.
Okay. Four. Okay.
Thank you.
I don't mind lying. Never. I didn't say that. Okay.
See you later.
All right. Take care.